Us to prove this summation equation using induction. Let's go. First up, n equals 1. Left-hand side is going to be the sum from r equals 1 to 1 of 2r minus 1, so it's going to be 2 times 1 minus 1 squared. I'm going to get 1. Then the right-hand side is going to equal a third times 1 times 4 times 1 squared minus 1. That's going to be 3. We're going to get 1 there as well. So true for n equals 1. This is us basically saying, right, we've got a domino. It's the first one, and it's going to start falling over. And now we're going to assume that this domino falls over later on, n equals k, and that it causes n equals k plus 1 to fall over. That's the idea here, and then it will all come together after. So assume true for n equals k. I'll write the exact same statement down, but from r equals 1 to k of 2r minus 1 squared equals a third k, 4k squared minus 1. Now we're going to show that this implies true for n equals k plus 1. So let's just write in brackets what we're trying to show. That this, now just putting k plus 1 up there, is equal to 1/3, and replace all the k's by k plus 1. K plus 1, then 4 k plus 1 squared minus 1. So let's start out with this here. So it's going to be the summation. Remember, I want to use this result to help me. So I'm going to do the summation from r equals 1 to k of 2r minus 1 squared. And I'm going to add on the term when I've got k plus 1 in there. So it'll be 2 lots of k plus 1 minus 1 all squared. And let's just work on that one by itself. That is then going to be 2k plus 2 minus 1 is going to be 2k plus 1 squared. And then using the result here, we can just replace this by a third k 4k squared minus 1. Using, I'll call it star. Right, so got rid of the summation. We've used that assumption that if it's true for n equals, it's true for n equals k. Now we've just got to try and get to here. Okay, so what I'm going to do is, well, let's just write this out again. Let's expand this bracket. I'm going to get 4k squared plus 4k plus 1 when I expand that double bracket. And it doesn't, this is not the easiest one that you'll ever see because, yeah, it's not like it all falls together quite yet. There's a bit of manipulation to do. What I'm going to do is factorize out a third. I think that's a good starting point. And then I'll multiply this bit out. So I've got 4k cubed minus k. And then I'll factorize the third out of here as well. So I just need to times this through by 3. 12k squared plus 12k plus 3. Tie that up, we get a third times 4k cubed plus 12k squared plus 11k plus 3. My aim now is to try and factorize to get this. Now you could divide the cubic through by k plus 1 using polynomial division, but I'm going to instead just take out a common factor of k plus 1 and then work out what must go in the bracket here and just check that it works. So this will have to be 4k squared. That will then guarantee me this term. I'll need a plus 3 here, which will guarantee me that term. I've got to make sure I get the 12k squared and the 11k now. Well, I've got 4k squared already. So if I do plus 8k here, then I'll get another 8k squared. So that term will be guaranteed. And if I now just multiply through to see how I get my k's, I get k times 3 to give me 3k, and 8k times 1 to give me 11k. That one works. So we're nearly there. So I'm just going to complete the square on it now. In fact, I feel like at this point, no, I think we should show our working. So it will be 4, then k squared plus 2k. We complete the square, that's what we do. And then 4 lots of k plus 1 squared minus 1. And finally, we're going to get 1/3 k plus 1, 4, k plus 1 squared minus 4 plus 3. So that's going to be a minus 1 here, which is exactly the same as this. So therefore true. You can arguably do this a little bit quicker in places. You can, you going from here to here. Yeah, you could take some shortcuts, but I want to show my working really clearly. It's just, yeah, don't leave any kind of gaps, actually, I'd say, just in case, they're part of the mark scheme, and argument just has to be clear at the end of the day. So, true for n equals 1, n equals k true implies n equals k plus 1 true. Therefore, by the principle, I always write this little bit at the end. Have your own way of doing it, but along similar lines of principle of mathematical induction, the equation is true for all, I think it was natural numbers n, was it? For all, oh, sorry, for all positive integers n. Well, that is the same thing. So back to my dominoes that I started drawing. We've shown that the first one falls over, and then if this one falls over, then the next one falls over. So the first one falling over means that the second one falls over, but the second one falling over means the third one falls over, and basically that is how our proof is working. The first statement implies n equals 1 implies n equals 2, n equals 2 implies n equals 3, and so on. So they all imply, basically it's implied for all positive integers n.